Okay, Assalamu alaikum everyone. Sorry, there was a problem with the permission access for the last tutorial. I don't know, so I had to delete it, I guess, and record this one again. But from now, I will try to see a solution for this problem. Maybe I will always upload the video for you, or we'll see something. But for now, we have the first problem. Okay, we have two problems, one with a normal Brayton cycle and one with a regenerative Brayton cycle. So this one is a cogeneration plant, meaning that it's just the normal Brayton cycle, but we are going to utilize or make some utilization where the turbine exhaust is not going to point one directly, but now it's going to a heat exchanger where we are going to generate some steam from this exhaust of turbine. Okay, so let's just recap. This is the PV diagram for the Brayton cycle, for the normal Brayton cycle. So this is point 1, and this is essentially point 2, this is point 3, and this is point 4. Okay, and if we do it in the TS diagram, so we have here TS diagram. This is point 1, this is point 2, this is point 3, this is point 4, and this is the cycle completed. So the temperature of point 4 here can be quite high sometimes. So what we are going to do, we're not going just to exhaust it, okay, to the environment and then come to temperature 1 eventually. We are going to use this turbine exhaust, okay, as in a heat exchanger to generate some steam. Because if we put this point 4 here, okay, point 4 will enter a heat exchanger, and then it's going to leave the heat exchanger, of course, at a lower temperature. And then here we insert water from in the as the other fluid in the heat exchanger. Maybe it's going to have a low temperature, maybe 20 degrees Celsius, and we can generate steam. So we can have here an outlet of water at 150 degrees Celsius, 200 degrees Celsius, whatever. So let's look at the problems and get the givings, okay, and what's asked from us to calculate. So we have at first the pressure limits, which are 100 kilopascal and 1000 kilopascals. So let's draw them here. 100 kilopascal, this is the lower pressure limit, which is the pressure of point 2 and point 4. Always memorize or the PV diagram of the cycle, okay, in this case, because you don't have equation sheets, or the equation sheets will be provided for you by the professor. So you have to memorize the cycles layout, okay? So these are point 1 and point 4, same pressure, point 2 and point 3, same pressure. And now the temperature limits are 20 degrees Celsius and 1186 kelvins. So this is point 1. And remember that or not remember, pay attention that the temperatures are not of the same unit. So don't just substitute directly. This is 20 degrees Celsius, which is equivalent to 293 kelvins. And this is 100 or 1186 kelvins, which is the maximum temperature in the cycle, which is 0.3. Look at it here, okay? This is the lowest temperature in the cycle. This is the highest temperature in the cycle, which is going to be 1186 kelvins. Okay, and now, of course, air is going to be the working fluid. Now let's look here at the combustion gases that leaves the turbine and enter the heat exchanger. Okay, remember about the utilization part that I told you about. Okay, so here from point 4, okay, let's draw the heat exchanger. Now we have a heat exchanger. Okay, point 4, which is coming from the turbine, with a temperature of, it tells us the temperature of the gases or the combustion gases that leave the turbine, 450 degrees Celsius, which is 723 kelvins. And let's draw it also here in the diagram, 723 degrees Kelvin, and it's going to leave at 350 degrees it's 300. Okay, 598 kelvins. 598 kelvins. Okay, and from here we have a water flow will enter at 15 degrees Celsius. We don't know the state, and it will leave at 200 degrees Celsius saturated vapor. Saturated vapor. And of course, we know that heat exchangers, each flow will operate on the same pressure because the heat exchanger cannot rise the pressure of the fluid. The only devices that rise the pressure of the fluid are, remember, compressor, turbines, or if we have a mixing chamber, because we are going to mix, not a mixing chamber, if we have a diffuser or a nozzle, okay, because we are going to change the pressure energy to kinetic energy and vice versa. So the only devices that can change the pressures are, as I told you, compressor, turbine, nozzles, diffusers, and these things. But heat exchangers, ducts, and also mixing chambers cannot rise the pressure of the fluid. So the saturated vapor here, we can get the pressure, saturated pressure. It's going to be P sat at 200 degrees Celsius, which I think you are going to find as 1,554.9, I guess, kilopascals, which is going to be the same pressure here. Okay, so P at this point is going to be the same as here. Go look on in the water tables or A5, okay, and you will find that the saturated pressure at 0.5 is much lower than the 1,500. So this is subcooled, okay, subcooled liquid. For subcooled liquid, we can make use of the approximation because we don't have A7 tables for the subcooled liquid. We can make use of the approximation H equal to HF at temperature. This is from thermodynamics, okay, approximately. And for air, we don't need the pressures because you know that the energy or the H, okay, is only a function of temperature. It's not a function of pressure. So if we have the temperature, we can get the enthalpy, and then we can calculate the heat transferred or the work or anything we need. And also an important difference between the Brayton cycle and the cycles that we dealt before, the diesel and the Otto cycles, is that this cycle is an open cycle. Okay, so we are always going to use enthalpies, not internal energies. In the diesel cycle, there is only one process like this with a constant pressure that we use enthalpies in it. Other than that, we use internal energies. But in the Brayton cycle, we are going to use enthalpies. Okay. So now, yeah, we finished everything, I guess. Yes, we have still one more giving, which is the net power produced by the gas turbine cycle. The power net, or W dot net, equal to 1,500 watts, kilowatts. And assuming that the compressor have an isentropic efficiency, the compressor is not isentropic, it have an isentropic efficiency of 86%, and the turbine isentropic efficiency of 88%. And we need to use variable specific heats, so it's not called air assumption. Okay, determine the mass flow rate of air. This is the first thing that we need to know. The back work ratio and the thermal efficiency of the cycle. The rate at which steam is produced in the heat exchanger, and also determine the utilization efficiency. The utilization efficiency, this part is not needed, but it is going to be the efficiency with the utilization process that we made here. Okay, so how more efficient or how efficient the cycle became after we included this process here. from the exhaust of the turbine. We are going to exchange it with some air, some water here, and we are going to generate steam. So this will increase the efficiency of the cycle. It's not increasing the thermal efficiency of the cycle. It will be the same, but it's going to make more energy or more benefit of the cycle. So it's going to raise its utilization efficiency called. Okay, it's not an important part, but just to show you that now the cycle have become more efficient. Okay, and yeah, that's it. So now the mass flow rate of the air. This is the first part. What's the equation for the mass flow rate? The mass flow rate, okay, equal always to the net work produced by the cycle over the specific work produced by the cycle. Okay, sorry, the net power produced by cycle over the specific work. Why is that? Because the power is in watts or in kilowatts, and the specific work is in joule or joules. Let me just put them as joules per seconds. And we know that watts, okay, or joules per kilograms. And we know that watt is joule per second. So what will happen? Watt will cancel with watt, kilogram will come up, and second will come down, okay? Because this is the denominator of the denominator, okay? So it is going to be rising up and per seconds. So this is the mass flow rate of air. This is the first. So it is asking us in a non-direct way to calculate the specific work of the cycle or the specific network of the cycle. What's the specific network of the cycle? It is work specific of the turbine minus work specific of the compressor, and which is also equal to H3 minus H4 minus H2 minus H1. Always do as that, because sometimes maybe you have problems that you need to solve that do not require you to solve for the whole cycle, okay, and get all the points. But in this case, we need to do that because, as you can see, we need all the points. But sometimes maybe you don't need all the points, and then you are going to waste your time by solving for all the cycle, and then you see here, and you don't need all of this information that you get at the first, okay? So always pay attention to that. Now we can get, I guess, every H from here. H1 is going to be using temperature 1. Here we have, it is 293. So H1, it is going to be, go to the tables. Now have 293 kelvins. Make interpolation between this H and this H to get the H in the middle, in between. I done the interpolation, and it's going to be 293.17 kilojoules per kilogram. So this is the first H. And to get the second H, because we don't have a temperature, we are going to make use of the isentropic process here. Okay, so go step by step. This is an isentropic process. What can we do in isentropic processes without having Calder assumption? We cannot use the TPK relationships. Remember them? The TPK relationships are like this: P2 over P1, and then you have here K minus 1 over K. These ones cannot be used. There is also two relationships like this. In variable specific heats, okay, or in a standard air assumption, we need to use the ratio relationships. What were the ratio relationships? They were, if we have an isentropic process, the relative pressure of 2 over the relative pressure of 1, it's going to be equal to pressure 2 over pressure 1, which is the pressure ratio, okay? This is what happens. Or if you flip this fraction, you can flip this also. So now we need pressure relative of 0.1. What's pressure relative of 0.1? Look here also in this table. It's somehow different from the table that you have, but with same values. Just have here notations to help you when delta S is equal to 0, okay? So when the process is isentropic. You can use these relative values, relative volume and relative pressure. Relative volume can be used in diesel cycle, okay, and in Otto cycle. Here we don't have compression ratio, okay, we only have pressure ratio, so we are going to use relative pressure, okay, in this case. So let's go also make an interpolation between those two values. It's going to be somewhere around 1.27, something like that. After I've done the interpolation, I've got that the relative pressure at point 1 is equal to 1.2765. Okay, it doesn't have a unit. This is the relative pressure at point 1. So I can get H at 2. Now relative pressure at point 2, which is the one that I don't know, over relative pressure at point 1, which is 1.2765, will be equal to 1000 over 100, okay, because this is the pressure at point 2 and this is the pressure at point 1. Stay consistent in the units. This is in kilopascal, this is in kilopascal, which is equal also to 10. So the relative pressure at point 2 will be equal to 12.765. This is the relative pressure at point 2. Go check again in the table where this relative pressure lies. So it's not here, it's not here. We cannot find 12 here. We cannot find 12. 12.7. So here, in between those two values. So temperature 2 is between 560 and 570. We don't need the temperature exactly. We need the H's because this is standard air assumption again. So we need to have the H of 0.2. What is H2? It's going to be somewhere between here. So it is going to be 566.47 if you done the interpolation. Okay, just put this value and you know how to do interpolation. So 5 pressure, H, okay, H2 is going to be 566.47. But remember something, this is when the process is isentropic, 100% isentropic efficiency. We have an isentropic efficiency of 86%, so we have a deviation. How is this deviation? Remember, this is 0.1, this is 0.2 when the process is done isentropically, and this is the process here when we don't have an isentropic process, okay? With the deviation, this is going to be 2 actual. This is 2 isentropic. What point we will use, or what point we use in calculations of efficiency and heat rejection and work and these things in the cycle? We always use the actual point, not the isentropic point, remember. The isentropic point is just there to help us know what is the actual point. We cannot get the actual point without the isentropic point at first. If the question tells you that the compressor is 100% isentropic, then H2S is going to be the same as H2A. Now in this case, they are not, so we need to account for this deviation. How are we going to do that? It is the compressor efficiency equal to, okay, or the isentropic efficiency of the compressor, H2S minus H1 over H2 actual minus H1. And now substitute H1 here and here, which was 293.17, 293.17. H2S is this, 566.47 kilojoules per kilograms. And we can get what is H2A. This is all equal to 86% because this is the isentropic efficiency. So H2A equal to 610 and 0.96 kilojoules per kilograms. So we find H2. Now we solved half of the problem, okay, because now we have this. We now know the specific work of the compressor. Now what's the specific work of the turbine? We do again the same steps, okay? Again, the same steps, just for the turbine side, not for the compressor side. Okay, just a minute, let me erase. And remember, you have two processes that are isentropic or can be isentropic with some deviation. So those are the points where you can use the relative ratios in this assumption, standard their assumptions. And you have two processes where the heat addition take place. So you cannot use, of course, the pressure ratios relationships in these two processes. Okay, you can use maybe the ideal gas relationships, maybe PV over T equal to PV over T, if you need to have one of the properties here. Okay, but now we don't need that because we have temperature of 0 0.3 directly and we have temperature of 0 0.4 directly. Okay, remember I denoted them here in the cycle. So temperature of 0 0.3 is 1186 kelvins and temperature of 0 0.4 is 723 kelvins. So from temperature 3, which equal to 1186 kelvins, go to the tables again, and where is 1000 kelvins and 100? Okay, I can find it here. It is between those two values. So my H is going to be around 1260, something like this. Let's check it. And after I've done the interpolation, it is actually 1261.38 kilojoules per kilogram. So this is H3. And temperature 4, which was equal to 723 kelvins, our H4 will be equal to 723, it's here. So our H, after I've done the interpolation again, is 738.061, okay, 0.061 kilojoules per kilogram. Okay, so this is kilojoules per kilograms for the H4. But now what at what or what's the state of this point? Is it actual or isentropic? That's the question. In the first question, I only had the temperature of 0.1, and then I assume that the process is isentropic. I get what's H2 for the isentropic process, and then I used the isentropic efficiency to know what's H2 actual. But here I have both temperatures. So what I'm going to do, if you have both temperatures, this means that this point is, of course, the actual point because he gives you the temperature. If this point was not the actual point, then no need to give you the temperature of 0.4. You go and then you calculate H4S, okay, using the same thing, using the relative relationships. Pressure relative 3 over pressure relative 4 equal to pressure 3 over pressure 4. Okay, and this is going to be 0.1 because this is, or it's going to be 10 because pressure 3 is 1000, pressure 4 is 100, and then you are going to divide those two. Okay, the pressure relative 4 you don't have, pressure relative 3 you get from the tables, and then again you go to the tables with this value to get what's H4S, and then you use the isentropic efficiency as we did for the compressor. But if he gives you the temperature directly, then no need to do that. Okay, if you want to check it, okay, let's check it for now. So we use this ratio, which is 10, and let's go and see what is the pressure relative of 0.3. Okay, the relative pressure of 0.3. Relative pressure of 0.3, it's going to be 226.94. Okay, this is the pressure relative 0.3. So the relative pressure of 0.4, it's going to be 22.694. Let's go and check at which enthalpy does this pressure relative give us. So 22.6. I can see that 22.6 is somewhere here. Yeah, it's somewhere here. This will give us a temperature of somewhere between 650 to 660. So let's say that it's 655. Okay, let's say that's 655. What's the temperature that was given to us in the problem? to 723. Yeah, this is obviously a higher temperature, and that's why this is the actual point, because again, this is point 3, this is the isentropic point, which is going to be point 4 isentropic, and this is the actual point. It have higher temperature than the isentropic point. So this makes sense, and this tells us that whenever we have the temperatures of both points, then that point is going to be the actual, because we don't need to do the isentropic thing and then divide and then get the pressure relative and then go. Okay, so remember this. I didn't use, so you can say as if the information given us in the question that the turbine have an isentropic efficiency of 88% is irrelevant for us. Okay, we will not use it because we have the temperature. And then now we can get what is the specific work. All of this is just for calculating the specific work. But don't worry, by now we have solved the cycle as a full totally, because we got all the H's. All the other things are now going to be application, just application. So H3, let's go and take H3, which was 1261.38 minus H4. Always use the actual values in calculations. Okay, that's why we always go for the actual values. Okay, minus H2, which we calculated before, again the actual one, minus the H at point 1, which is 900 and or 293.17. So this is going to give us the specific work, which is the specific work. It's going to be somewhere or somehow 1000. Let me do the calculation for you. You can also do it to follow me if you want, and to or solve the question as a practice. Okay. So it will be 205. 205.59. Okay, just check with me. So if I didn't do any mistake, okay, in the calculations, but I believe that the H's are correct. Okay, so this is kilojoules per kilograms. Now, what's the work? The work is going to be, or what's the mass flow rate that we want to find? As we said before, it is the net work or the net power over the net specific work. 1500 kilowatts. Okay, keep them both in kilos, so you are going to get kilograms per second. Or if you want, you just can convert to SI directly. We now know that the mass flow rate of air is 7.3 kilojoules per second. This is the first giving. The second giving, or the second thing that asks from us to calculate is the back work ratio. The back work ratio is always the specific work of the compressor over the specific work of the turbine. Or we can use the total or the net or the power of the compressor over the power of the turbine if we have powers. Okay, but now we have specifics. Okay, so we can use them. Again, H2 minus H1, and here H3 minus H4, and always use actuals. Okay, these points don't have actuals or isentropic because they are the beginning of the process. These are the ending of the processes, point 2 and point 4. So you are going to end up with just substitute all these 4 values. Okay, let me substitute them again for you here. So we are going to have 126.38. Oh, this is for the turbine. 126 1.38 minus H4A, which we calculated 738.06, okay, over this values 610.98 minus 293.17, I believe, yes, 0.17. So now we are going to get the back work ratio, which is a fairly 60%, I guess, 0.7. Okay, 60%, 0.7. This is the back work ratio. This is the amount of, or the ratio of the work that will be used again to power the compressor. Because if we draw this cycle, let's say that this is our turbine and this is our compressor. Okay, just a fair sketch or a full sketch. So the work that's going to be produced from this turbine, a fraction of it is going to be used to power the compressor. And another fraction is going to be used in making some electricity, generate anything else that we need to have. Okay, so this is called the network. The network is the work of the turbine minus the work of the compressor. And the back work ratio is the amount that we will get back and power the compressor by. Okay, so it is always the compressor over the turbine because the compressor work is lower than the turbine work. And then the final thing, or not the final thing, we have two steps. We have to calculate now the flow of water. What's the mass flow rate of water or of steam production? This is very easy. This is a question from thermodynamics, okay? Because now you will solve the heat exchanger problem. Till now, we didn't touch the heat exchanger, the thing that makes this utilization. This thing is only required for part C. Okay, remember the thing that I did for you, and we need to know this is saturated vapor, and then I knew how this is a subcooled. Okay, this is coming from the utilization here, 0.4. It's not directly connected to 0.1. 0.4 will be now will enter a heat exchanger and make a utilization here where we are going to generate steam in this cogeneration plant. Okay, so what is the mass flow rate of water here? Remember, use the principle for heat exchanger because this heat exchanger is 100% efficient. So the heat that's going to be rejected from the air stream is going to be fully received by the water stream. So Q dot, okay, Q dot out from the air is going to be equal to Q dot in for the water. And then what's Q dot out from the air? It is, of course, M dot H in for air minus H out for air. And here we have M dot, again the same thing, but for the water, let's make it H out minus H in. Why? Because out is higher than in, okay? Or otherwise you can put a minus outside and make it N minus out. So H in for water, sorry, H out for water, out for water, minus H in for water. And here we have the mass flow rate of water. Here we have the mass flow rate of air. We've calculated before the mass flow rate of air, which is 7.3. We know Hn for air, which is 702.3 kelvins is temperature, and we got the enthalpy associated with that, which was 738.06 kilojoules per kilograms. And what is H out? H out, we are going to use this temperature, 598 kelvins. So go to 598 kelvins again. Okay, I'm doing this just to make you used to the tables. So where is 598? Okay, 598 is going to be somewhere between here, actually very close to 600. So we're going to get a very close enthalpy value to this. What's the enthalpy value? It's going to be 604.92 if you do the interpolation. 604.92 equal to m dot of water, which I don't know, and then open the brackets. This H we are going to get air table from the water tables, A4. This is saturated vapor. So what you have, you will use Hg directly, Hg at this temperature. And this is subcooled. How we know? We know that the pressure is constant for this flow because this is a heat exchanger device. Take the saturation pressure of this point, go with it backwards because it's the same pressure. Use this pressure and temperature to determine the state. State is subcooled. Now, because subcooled, we don't have values, so we make the approximation. Approximation at temperature, not at pressure. You'll get a wrong value if you put at pressure. It's at temperature. So I got these values from the water tables, which were 2,000, okay, and 792 minus 62.98. So the mass flow rate of water obviously is going to be very or much less than the mass flow rate of air, because the difference in enthalpy here is very huge. So the m dot should be less to make those two expressions equal. So now the m dot of water, which is part C, is going to be 0.36 kilojoules per kilograms or per seconds. Okay, just very simple, the Brayton cycle that we know, but now here with an additional heat exchanger problem from Therm 1. Just remember that the pressure is going to be the same thing, okay? And yeah, we need to find the plant efficiency. Yes, the plant efficiency, thermal efficiency, will be equal to what? The plant thermal efficiency, it's always 1 minus Q out over Qn, or you can say that it is Q or work, okay, net over Qn. Okay, and if you want to make it capitals, okay, you're gonna put it here, work or the power net over Q dot N. What's easier to use now in this case? I guess it's this one, because already we have from the problem that the net power produced is 1,500 kilowatts. Yeah, it is here kilowatts. So just calculate Qn dot. So we need to multiply by the mass flow rate, which is 7.3. We got it before. And what's Qn? It is H3 minus H2. Okay, which H2? H2 actual, as always. So we are going to get 1 here, okay. Let's substitute the values, okay. H3 was 1,600, 200 point, okay, 38 minus, and then we have H2, which was 610.96. Okay, let me substitute that for you. It's going to be 31%, okay, 31.6%. This is the thermal efficiency of the cycle. Now, the thing that I told you is not important, but I will do just to make you see how this utilization process made the cycle more efficient. So it's going to be called the utilization efficiency. Okay, let's call it epsilon for now. Okay, the utilization efficiency. Utilization. So it is going to be the work dot net of the cycle plus the utilization energy, okay, which is the heat received for the water, okay, or it can be the heat rejected from the turbine exhaust, okay. You can do both because they are the same, over Q dot N. Of course, we are going to put this number here, increase it, add it to the work net, the efficiency will increase. So let's do it here, okay. It is going to be, or let me divide it here, make it somehow mathematical. We calculated this ratio, which was 31.6%. Let's calculate this ratio, okay, and add it to it. So it is going to be m dot for water, which was 0.36, multiplied by the difference in enthalpy for water, here over Qn, which was the same number as here. Okay, if you do it, you are going to get somehow 52%. Okay, you see the increase in the efficiency that this utilization process made, but you're not going to ask about this utilization efficiency, or you are going to give you be given the equation for it and then you calculate it. Okay, but you don't have to know from yourself that the utilization efficiency will be like this. Okay, and yeah, so that's it. There is a problem, I think, in the slides where this thing happens, I guess, but not with the Brayton cycle. I think with the Rankine cycle, chapter 10, but it's the same principle, okay? Sometimes we can use the exhaust of this point, the last point in the cycle, and then put it here with a heat exchanger, okay? Because essentially this process here will go with a heat exchanger because the temperature of this point is not going to drop there like this. But sometimes we don't care about how is this point cooled, okay? So we don't use the heat exchanger. It's not even used in the calculation of the efficiency. It's used if you want to calculate or calculate the mass flow rate of the fluid that's going there, okay? So it's just an additional problem to the actual problem. But it doesn't need to be solved, okay, in order to solve the cycle problem, the main problem. And just a side thing there to calculate. Okay, so yeah, I guess by this is maybe this is the hardest version of the normal Brayton cycle, where we made some utilization there. But again, there is nothing else. You just are going to be given a Brayton cycle with the cold air assumption or a standard air assumption, maybe like this one. If it's called air assumption, then there is no need to go to the tables. And as I told you in the last tutorial, you are going to use the relative relations and get everything done. So yeah. Now, this is the problem with the regeneration. The Brayton regeneration cycle, it's also a modification of the Brayton, where we make some utilization, but this utilization will be inside the cycle, okay? So it will affect the thermal efficiency of the cycle directly. Why? Let's see how. Okay, so, and this is a one with cold air assumption. So you get used to both approximations or both assumptions for air. Just sorry for taking time to delete this. Okay. Now we have a gas turbine. Also, I added this or I changed the temperature here, the maximum temperature in the cycle, because there was something in the physical meaning of it. Okay, because if you, let's see here, this is the TS diagram. Okay, and this is point 1, this is point 2, this is point 4, and this is this is point 3, and this is point 4. So what happens basically in the regenerative Brayton cycle? We are going to take this stream here, this stream, and exchange it with this point, okay? So we want to further increase the temperature here, okay? So maybe we move it to here, and this point will be called 0.5, and this point will maybe move to here, and it will be called 0.6. So the heat addition, the actual heat addition process from outside the cycle, from the source, maybe it's going to be furnace or cold or anything from outside, it's going to be only here. So we decreased the heat addition to the cycle, which will increase the thermal efficiency, because the thermal efficiency is the work net produced or the power net produced over the heat rejected. So the work will stay the same. This is the work net. Depends on these and these two lines. But the heat addition depends on this line, okay, from here to here. If we exchange heat between this point and this point, then this heat addition will take place inside the cycle. It's going to be an internal process, so we don't add the heat here, okay? The heat addition here will not be accounted, so only this fraction. So we decrease the heat addition, which meaning that we are increasing the thermal efficiency. That's about the theory. Let's just solve the question directly, okay? We don't care much about that, but just to recap for you, okay? And yeah, okay, I was talking about this point. So this point to have this thing work, okay, efficiently, okay, to have this thing work efficiently, we need 0.4 to be higher than 0.2, okay? We need 0.4 to be higher than 0.2 because, of course, if 0.4 have a less temperature than 0.2, then 0.2 temperature, what will happen to it? It will decrease, and 0.4 temperature will increase. And we don't want this thing. If this point temperature decreased, okay, it went down, then yeah, like this. So now we are increasing, okay, we are increasing the heat addition, okay, we are not decreasing it. So this will not make sense. I don't know why the problem was made like that. I guess just to solve and substitute the numbers. But if you thought of it, or if you want to calculate the regenerative efficiency, we'll find it above 100%. Okay, which is something that cannot happen, of course. So I just changed this temperature a bit so you don't get confused by the problem formulation. But again, it's the same thing. Now let's start. A gas turbine for an automobile is designed with a regenerator. Okay, air enters the compressor of this engine at 100 kilopascals and 30 degrees Celsius. So this is point one. Point one here, we have the temperature for that point, which is 30 degrees Celsius, and also pay attention, use kelvins always and use consistent units. So this is going to be 303 kelvins, okay, which is 0.1 in the cycle. And now we know that the maximum or the maximum cycle temperature is 950, which is 0.3 up there. Is going to be 950, so this is equivalent to 120 or 1200 and I think 100, okay, yeah, 1223 kelvins. Okay, just add 273, and this is 0.2. This is 0.5 in between, or maybe not in between exactly. This is 0.4. This is 0.6 and this is 0.1. Okay, just make yourself used to the diagrams, because the devices sketch is not going to be given to you. You have to extract the information by yourself. And the pressure ratio is 10. He tells you that the lower pressure is 100 kilopascals. So here, this whole pressure, this is a constant pressure process, remember? This pressure, all of it will be 100 kilopascal. So the upper pressure is going to be 1000. Again, why? Because the pressure ratio is 10. If we do this in the PV diagram, okay, something like this, something like this, and something like this. So this is going to be 0.6 and this is 0.5. This pressure is 1000 kilopascals, and this pressure is 100 kilopascals. Okay, this is the V, this is the P. So I guess we finished by now. The only thing, yes, this is the important information given to us. Either he gave us the regenerative efficiency, or he gave us an information that will help us solve for these two additional points that we get. Okay, what he tells us that the cold air stream leaves the regenerator 10 degrees cooler than the hot air stream at the inlet of the regenerator. So where are the cold air stream and where is the hot air stream? Remember, 0.4 temperature should be higher than 0.2 temperature, as I told you. So this is the cold air stream. From 2 to 5, this is the cold air stream. And from 5 to 6, this is the hot air stream. So he tells you that the cold air stream leaves the regenerator 10 degrees Celsius cooler. Okay, so 0.5 temperature is 10 degrees cooler. Okay, so minus 10 degrees. From which point? Let me know. Cooler than the hot air stream at the inlet of the regenerator. So here at the inlet of regenerator, which is 0.4. So temperature 5 is lower than temperature 4 by 10 degrees. Okay, let me draw the cycle sketch for you. I'm afraid that you might get confused. So this is the compressor. Okay, this is how we draw the compressor, and this is the inlet. Okay, here this is point 1. It enters the compressor. Now, instead of going directly to the combustion chamber, I have here a device that's called the regenerator. Regenerator. Okay, and then this is point 2. It will enter the regenerator, and then from the regenerator, it's going to leave for the combustion chamber, the combustion process. Okay, this is point 5. This is point 3 here after the combustion happens, and then we go to the turbine, of course. We generate our work here, okay, and then this is point 4, and then the outlet here, point 4, it's going to enter the regenerator, okay, and then leave as point 6. Okay, leave the generator, and then from 6 here we can go to point 1. Okay, maybe it's going to exhaust it here to the air. It's going to mix with the environment air to go back again to point 1. Either ways, we don't care about this process unless that we have the temp or just that we have the temperature of point 6, we have the temperature of point 1. So now we know the heat rejected, okay, between those 2 points. I don't know if it's utilized in a heat exchanger. I don't know. And we don't care actually about that in this problem, but we have temperature here and we have temperature here. Okay, we don't care about the connection between them. So yeah, so now the temperature of point 2 is going to be low, okay, and the temperature of point 4 is high, so we want to make use of it inside the regenerator. So heat is going to be flowing in this direction. Okay, so he tells me that the cold air stream, which is this one, I'm going to denote it in blue, the cold air stream, and the hot one, I'm going to denote it in red. Okay, this is the hot one. So the cold one here, 0.5 stream, leaves the regenerator 10 degrees cooler than the inlet of the hot stream. So how can we interpret that in numbers? T5, okay, equal to T4 minus 10. It is 10 degrees cooler than that point. So yeah, that's it. And there is another thing in the regenerator, okay, the regenerator. What's the amount of heat that was saved? Of course, the combustion in the combustion chamber, we are going to have the heat addition. So what's the amount of heat that was saved? This amount of heat is the amount that was saved between 5 and 2, because we added using the regenerator, not an external source, okay? Using the regenerator and not an external source. So this amount was saved, okay? So you call that use this equation, or sometimes we are going to use it, that Q regenerated is the same amount as Q saved, okay? Q saved. Okay, it doesn't matter if you call this one regenerated and this one saved, or this one saved and this one regenerated. At the end, they are going to be the same. Okay, so some heat taken from here, gone to here from inside the cycle. Okay, so it is going to be H, or not H's in this case, because we have cold air assumption. Okay, it is going to be Cp. Okay, delta T, which is T5 minus T2, equal to Cp T T4 minus T6. And of course, we can cancel the CPs in this case. Remember, this is only because we have cold air assumption. If we had standard air assumption, we need to use the H's. And then T5 minus T2 is equal to T4 minus T6. Okay, this is the relation. Maybe sometimes we are going to need 0.6, so we can calculate the heat rejected, because this is the heat rejected here, Q out. So sometimes we can need the temperature of 0.6. Maybe we need it in this problem. Let us look. All this talking without seeing what the problem is asking for. But yeah, so determine the rates of heat addition and rejection for the cycle. So we need Q out and we need Q in. And he tell me the rates of heat rejection and heat addition. It's not the specific heat. So I need to multiply by m dot and m dot of the cycle to get Q dot out and Q dot in the cycle. Do I have the m dot? No, but I have an information just like the one before. I have the net work produced, the net power produced. And when I have the net power produced, I can calculate the specific work produced and then divide them together to get m dot. So our first task is getting m dot of air as the first question. Work.net over work net small. This one is 115 kilowatts, and this one, now look at this, it's going to be easier for us because it's CP T4 minus T3, the turbine. Okay, the turbine work T3 minus T4 because 3 is higher, always the higher minus the lower, minus CP T2 minus T1. This one is the compressor, so this one is compressor, always turbine work minus compressor work, equal to, do I have the temperature of 0.1? Yes, I do. Do I have the temperature of 0.3? Yes. Do I have the temperature of 0.4? Actually, no, we don't have the temperature of 0.4. And we don't have the temperature of 0.2. But what we can do, these two processes are isentropic. Does he give me any isentropic efficiency? No. He told me that assume both compressors and turbine to be isentropic. So they are 100% isentropically efficient, meaning that I'm not going to bother by getting the values again for the isentropic and then the actual and do these stuff. So just directly apply. Now using the TPK relationships, why is that? Because we have Calder assumption. So yeah, T1 over T2 is going to be equal to P1 over P2. Okay, no ratio relationships, remember. 1.4, you are not going even to use the tables, okay? So now just delete the tables because this is called their assumption again. And keep repeating that just that you don't forget it. And temperature, pressure 1 over pressure 2 is 0.1 because it tells me that the pressure ratio is 10, and then pressure 1 over pressure 2 is going to be 0.1, okay? The pressure ratio is the higher over the lower, and now I'm dividing the lower over the higher, so it's going to be the reciprocal, 0.1. Temperature 1 is 303 over temperature 2, the one that I don't know, I want to calculate 1.4 minus 1 over 1.4, and now I get my temperature 2, the actual one, which is equal to the isentropic one because I have a 100% isentropic efficiency. It is going to be 585 kelvins, okay? If I have an isentropic efficiency other than 100, maybe let's say 90, so what I'm going to do is, instead of H's, just put T's, okay? So T minus T over T minus T is going to be T1, T1. It's going to be T2 S isentropic, and this is T2 actual, okay? But now I have 100%, so they are going to be the same. So this is T2, and then again the same thing to get T4, which is T4 over T3 equal to pressure 4 over pressure 3. Okay, so and then to the power K minus 1 over K, which is going to be 1.4, 1.4, unless specified otherwise, unless specified otherwise. P4 is going to be, yeah, he told me that the pressure ratio is 10. So P4 over 3, it's not 10, it's 0.1 again. You can do it maybe this time. Let's just do it this time just to change it. Okay, T3 over T4, pressure 3 over pressure 4. Now this one is going to be the pressure ratio, which is 10. So 10 to the power 0.4 over 1.4. And here we have temperature 3, which is 3 kelvins over T4. Okay, so calculate T4, which is going to come as 633.45 kelvins. So this is the temperature of 0.4. Okay, now substitute everything there in the equation. Where was the equation? Where did I miss it? Yeah, here. Okay, I'm afraid that everything got mixed up, so let me delete from here. Okay, We calculated everything that we need. Delete. Okay, sorry for that. So here, let's put it again, okay, to be clear. Okay, it's not part A, it's the part that we need to calculate the mass flow rate of air at first to multiply it by the specific heats, okay, because he is asking for the heat rates. And this was 100K and 15 kilowatts. I need to put here work turbine minus work compressor to get the work net. So what was work turbine? It is CP. Now CP is constant at room temperature, or he can give you a value to use. What is the temperature difference in the turbine? It is 1223 minus 623.45, okay? Or sorry, 633. I put it as 23, I think, before. It's 633. And then here minus 1.005 again for this one, for the compressor. And temperature 2 for the compressor is 585. Temperature inlet to the compressor is 303. And now we can get of course, these specific heats are in kilojoules per kilograms. Okay, are in kilojoules per kilograms, So no need to convert this kilowatts. The mass flow rate of air is going to be 0.372 kilojoules per seconds, kilograms per seconds. Why am I missing the units now? Okay, so what's left? Calculating Qn and Q out. Then to multiply them by the m dot. So what's Qn? Remember that we saved some of the Qn. So it is not anymore CP T3 minus T2. No, we moved point 2 a little bit forward to be T5. Okay, and also for the Q out, same thing happened. Instead of it being T4 minus T1, point 4 moved a little bit downward to be 0.6. Okay, here from this sketch. Okay, point 2 moved a little bit forward, point 4 moved a little bit downward using this regenerator. Okay, I'm not going to explain it again, this theory part. Okay, I don't know if you did understand it at the first time. If you don't understand it, always feel free to ask me by email or anything. But again, to apply the equations for them, just change the T4 here to T5 and the the T3 here to T5 and T5 here, T4 here to T6. Okay, T3 to 5, T4 to 6. So let's just calculate. T3, I know it. It is 1, 2, 2, 3. Again, from the question, the 950 degrees Celsius, that's it, the maximum temperature in the cycle. T5, yeah, so remember that we said, or we were given this thing in the problem. We calculated T4 using the TPK relationships. It was 633.45. So just subtract 10 degrees. So we're going to get T5 as 623.45. CP, of course, is known, which is 1.005. And now T1 is known, which is 303. It is given in the problem. Kelvins. What is T6? Use this principle, the second principle that I told you about. This one, that Q regenerator is equal to Q saved. T5 is known. T2 is known. T4 is known. T6 is left. Cancel those two, okay, CPs and CPs. So T6 will be equal to T5 minus T2 minus T4. Yes, T5 minus T2 minus T4, and this is minus T6. So if you multiply by minus, you are going to get positive, and here also positive, and here minus. So T2 plus T4 minus T5. This is going to be at the end 595 kelvins. So just 10 degrees higher than T2. Okay, because remember the difference between those two temperatures was in the beginning given the problem, which was 10 degrees. Okay, but again, you don't need to use that. Just add the numbers there blindly, or if you want to make use of it, do that. So now, yeah, 595. Memorize this number, substitute it here, 595. Can now we get Qn and Q out? Yes, we can. Does Qn at the end will be, I did them here, okay, 602.55. Cp, T3 minus T5. Okay, Q out, kilojoule per kilogram, don't forget the units. T out, again, Cp, T6 minus T1. So 293.46 kilojoules per kilograms. Multiply both by m dot of air, which we calculated before. Multiply this and this. Here you are going to get Q dot in, Q dot out, capitals. It is now 4.15 kilowatts. Now this is the new unit for the heat rate, okay, and kilowatts. Yeah, so that's the problem. Just want to make a fast check if you want to make that. Remember that the work net, it's not only the turbine work minus the compressor work. You can do something as the Qn minus the Q out. This is something that you took in chapter 6 in thermodynamics, okay? Just to make sure that it is should be 115 okay, kilowatts, the one that we began with given in the problem. If you subtract these, I believe you'll get 114.9, which is fairly close to this value. Okay, just from the approximations, the little approximations that we did, we take two numbers after the decimal, or you take three numbers after the decimal, but it should be the same if you took all the numbers after the decimal. Yeah, so that's it. Maybe if I let me just for to make you confident about this stuff, if we want to calculate the thermal efficiency, okay, of this cycle, so it will be what? It will be 1 minus Q dot in out over Q dot in. Yeah, you can do that. You have those two values, or you can use a direct equation for the cold air efficiency. Okay, you can use a direct equation to calculate the cold air efficiency of the cycle, because this is a cold air cycle, remember? So you can use a direct equation to calculate the cold air efficiency of the regenerative cycle. Okay, I believe this equation is does depend on the relative pressure, or the pressure ratio there, and also the temperatures, okay, of the cycle, the temperature bounds of the cycle. Just look it up there. It should be in your book, I guess. But let me see here if I have the equation or if I note it down. Okay. Okay, sorry for this. The thermal efficiency for a cold air cycle, this is only for cold air cycle, regenerative Brayton one, regenerative Brayton. It will be 1 minus T1 over T3 multiplied by RP, okay, the pressure ratio, to the power K minus 1 over K. T1, T3 having pressure ratio is 10. This is 1.4. And this is 1.4, so you can calculate the thermal efficiency of the cold air Brayton directly, or just use those two. Okay, not only for the cold air Brayton, for the cold air auto, for the cold air diesel, also for the cold air dual one. I gave it to you in the last tutorial, and they solved in the detail solved problem. And yeah, that's it. If you want to calculate now the regenerative efficiency or the regenerator efficiency, it is defined as H5 minus H2 over H4 minus H2. So you can cancel the H's because this is a colder cycle. So you are going to write a CP over CP here. Cancel CP's, both CP's. So it is T5 minus T2 over T4 minus T2. Okay. Let's calculate the regenerator efficiency for this cycle. Okay. So sometimes you might not be giving this here, this information. This information helped us to calculate T5 and T6. You might be given the regenerator efficiency. And then the regenerator efficiency will help you to calculate T5. And then from T5, you are going to calculate T6 using the principle for the regenerator. Okay. Remember, we solved the first problem using the heat exchanger. Remember, I told you Q is equal to Q. The regenerator is a heat exchanger at the end. So it's the same thing. Q is equal to Q. Okay, Q from 5 to, or from 5 to 2 is the same as Q from 6 to 1. Not from 6 to 1, to, Q from 5 to 2, the same as Q from 4 to 6. Okay, so it is the same thing. And then from this, you can calculate temperature of 0.6. So now let's just calculate the regenerative efficiency, okay, to make you confident about that. Everything in the cycle you can do. T5 is, T5 was, what was it? Okay. T5 of the cycle. Oh, where was it? Okay, it was 623.45. Okay, it was 623.45 minus T2 of the cycle, which was 585. Okay, T4 of the cycle, which was 633.45. This is the one that we subtracted 10 degrees to get T5. And then T2, which is 585. Now the regenerator efficiency is minus 585. It is 79%. Okay. And remember something, or just observe something. If the regenerative efficiency is 100%, this means that T5 is equal to T4, because T2 is T2. Then if T5 is equal to T4, this is the maximum efficiency we can get from the regenerator. The TS diagram for that is going to be like this. This is 1, this is 2. That is 3. Okay. And you see this is 5. Okay. So 0.4 is going to be here. Okay. Here. T4 is going to be the same as T.5. And then here this is 0.6 and this is 1. Okay. So if 4 and 5 were on the same height, now this is the maximum efficiency we can get from the regenerator. Okay. And then of course 0.5 is going to be lower than 0.4, maybe somewhere here, somewhere here, somewhere here. That's why we have the regenerative efficiency is less than 100%. Okay. So yeah, that's it. I hope that you understood those two problems. Okay, I'm going to upload the file there for you with the video, and see you next tutorial, inshallah. Assalamu alaikum.